Cool, welcome everyone. Thanks for making it to a 4 p.m. session on the first day. I'm really, really glad you're here because it truly is an effort at this point in the day. So today we'll be talking about highways and hexagons. This is a presentation that came out of our project that we've done with our clients. On stage here, you'll see myself from Mantle Group. We are a consulting partner with Databricks in APAC. We do consulting all across different clouds. We provide sort of premier tier consulting for Databricks as well. There's a lot of us. There's about 900 of us in APAC and a whole bunch of specialists as well. I'm here today with Olivia from Databricks. She's representing Austroads, who unfortunately couldn't make it to the session today. But yeah.
Cool. So let me introduce my customer, Austroads, in this presentation. They're based in Sydney, Australia. They're the transport agencies for Australia and New Zealand. Their mission is to provide national service that helps transport operations run smoothly across the state borders. So within Austroads, TCA functions as subsidiary and center of excellence, focusing on the certification and technology in the transport sector. So how does the telematics ecosystem actually operate? It all starts from the manufacturers. So manufacturers, they produce the GPS and telematics devices designed to capture the vehicle data. Things like how the speed they're driving on, what's the location they're at, operational performance, etc. But before these devices can be installed into the vehicles, they must pass rigorous testing that TCA sets for them. So TCA sets strict standards for performance, reliability, and safety. And only once the certified devices has been passed the test, they will be installed on the vehicles. And once installed, devices get to work actually collecting the real-time vehicle data. This data is then being transmitted to Austroads via TCA, where it's aggregated and enriched. And from there, Austroads make this data available, not just to the government agencies, but also to the industries and also the commercial organizations. So the data that we collect through this process are the following. The main ones are the last three ones when we're talking about the position information, vehicle weights, mass information, as well as the road network access information. So why do we need to collect this data and who is interested in it? Let's start with the National Heavy Vehicle Registrator, NHVR. So in Australia, if you want to drive a heavy vehicle, you need to have a permit. And that permit defines the pre-approved routes for the vehicles to follow. So for the compliance and informant's purpose, NHVR need to be across the roads data and the usage patterns to ensure the trucks are actually on their permitted routes. Next, we talk about the road infrastructure managers and local government agencies, LGAs, authorities. So they use this data to understand how their transport networks are actually working, things like roads, the bridges, and other assets. So why is this important? Because it's actually directly related to the risk and infrastructure integrity. So imagine you're a console engineer. You design this bridge that is supposed to carry like 300,000 trucks every year. But then Austroads data reveals that it's actually covering 600,000 trucks each year. So that actually doubles the load, which means that the bridge is gonna wearing out much faster than it's supposed to be, right? So, and that poses a significant safety and maintenance risk. So there are two different source systems that Austroads has been using since 2019. As one was decommissioned, they adopt another one. So, but looking at the data volumes combined altogether, it's not hard to find that we have the challenge of the data scale over time. They are expecting to have the telematics devices increasing from currently 35,000 to 90,000 in the future for the coming 5 years. So that means the data platform that we designed has to be robust and scalable enough to handle 3 to 5 times of the current data volume. So how the data is flowing through the Austral's data management system. First of all, you have the TCA receives the telematics data ranging from different frequencies. It can be from near real time or monthly loads, and they ingest the data and do quality checks to make sure only the high quality data is then moved towards the analysis. Next comes to the geospatial matching in the middle. This has done in the multiple levels, from the roads to localities to states, and even for specific point of interest. Finally, the data is aggregated and prepared for reporting, and then it can be presented in the Esri ArcGIS for the end user. So there are 5 different types of matching that we have in this situation. But for the purpose of this presentation, we're only focusing on the road and LGA matching. So this is the current design. At technical level, we have all the different types of the data that is covering the location, routing, the boundaries, and mass in different formats coming in GeoJSON, JSON, XML. They've been ingested into Databricks data intelligence platform. And then currently we're using Shapely and Databricks H3 functions to process the data. This is where your data engineers and data science get to work in the same platform on the same set of data for pipeline development and model development. After data has been standardized, aggregated, and enriched, DAs then can pick it up and start to query the data from DB-SQL. It can also be pushed to Power BI, RapidMiner, and ArcGIS for the end user. So most of the heavy lifting of the matching happens in the middle. I'll hand it over to Peter to talk about what challenges they encountered and how they tackled them.
Thanks, Olivia. Cool, all right. Now that we have a bit of a background and we know why we do this and why even bother with this problem, let's talk about matching, the problem of road matching, LGA matching. And if we think of it, the problem could be broken down into 3 steps. There is the problem of just matching to a single geometry. There's a problem of matching to multiple geometries and multiple locations. And there's a problem of getting it to production, which is mostly a boring thing for everyone who ever developed code. Anyone here who used H3 before? Cool, lots of hands, that's good. I won't be spending too much time introducing it because it's hard to introduce matching without H3, so it's kind of a catch-22. But yeah, let's look at the matching problem and let's distill it into what it actually is. So first of all, we get a set of data that comes in from our trucks that drive from sort of locations, say A to B, and that data comes in with a whole bunch of metadata, but essentially it's just latitude, longitude points that we care about. On the other side of the stream, pipeline, stream is reserved word. On the other side of the pipeline, we've got geoscape maps, and these ones come in as, you can imagine them as different layers of the system. You've got your state maps, you've got your LGA or council maps, you've got your localities, roads, and so on. And they come as GeoJSON geometries, which is a format you're probably familiar with. And then we've got a problem that we need to solve. We need some sort of algorithm that can figure out, join the two together, and give us an answer of that a given truck was in a given location, it was in a given council, it passed through a set of roads, and so on. You can obviously scale that to any kind of points of interest that you're interested in, or any things like bridges, motorways, and so on. All right, so if we kind of visualize our problem, first of all, we've got our position data that comes in. That's our latitude, longitude points. Here I've plotted them against a very dear to me park in Melbourne. A fictional truck traveling down them. So while we get these points, in the other set of data, we get our geoscape roads. These come in as line strings. So they're essentially arrays of sets of points, and they're separated into 200-meter segments. So while you might see here on the map, you might see this as a single line. It actually is a whole bunch of segments that we get, which creates a bit of problems when you process it, but such is the data that we get. The other data set that we receive is LGAs, or councils, and this creates boundaries between sort of different authorities in Australia. These come as polygons, so they create a full shape. And it's still just an array of points, and if you kind of trace them together, you'll get a full polygon. These are quite large. They come in, on average, at 2,700 points, so they're fairly heavy objects when you start working with them. And the reason for that is they become very complicated geometries. You can see that if you were to just draw a square, you'll probably need 4 points, but if you need to draw something that represents a natural boundary, such as body of water or something like that, you would need a lot of points to kind of draw out that shape. All right, so one of the things that we do straight away that once we receive the data, we try to convert it and compress it. The reason for that is, again, we receive large geometry objects with lots of spaces. They're great for human readability, but just by converting them to a binary format, we compress them 2.5 times. And from one side, you can think of it as, yes, you reduce the amount of storage that you store on your platform, but at the same time, compressing it into a binary format reduces your memory load, because once you start processing that data, there's less to kind of sit in your memory. It reduces your I/O, so while you're reading, it's quicker because you're reading less data. And obviously, it reduces any kind of transformations between different nodes on your Databricks on your Spark system, because they don't need to travel through your network, or at least 2.5 times less data needs to travel through your network. So once we talk, now that we have kind of an idea of what matching is, there's a few approaches to it. In essence, it's kind of a scale. You start at the left-hand side, where you've got index-centric approach, and what this does is essentially splits your map into a set of indexes or bins, and it gives you an approximate estimate of where your data is located. On the opposite side of that, you've got traditional sort of spatial analytics. Some of you who have used spatial analytics in SQL Server, you might know them as SD functions. These ones, they give you a lot more precision, obviously, because they're mathematical computations. They give you explicit answer for your requirement, but they are very compute heavy. So essentially, your trade-off is between accuracy and cost of compute. What generally people have come up with is a in-the-middle approach, which is the hybrid approach. And this is what we're going to talk about today, and how we've set that up. So just before we jump into that, a high-level overview of H3. So here you can see there's a few levels of resolution. What H3 does, it's a set of hexagons. It's a way to split your map into a set of hexagons, and these hexagons have a hierarchical structure. So each resolution has a child resolution underneath. So a hexagon will have hexagons inside of it, and it makes it easy to navigate up and down the scale of the system that you work with. Why do we need to split your data into hexagons? Well, the reason is that it allows you to join across disparate data sets really easily. It gives you this, it gives you an ability to work in the same universe, in the same kind of types of object. And probably the final question is, why bother with H3? Simple answer is it's developed by Uber, so it's got to be good, right? But a real answer is it's really well integrated in Databricks. It's almost seamless. It runs super well. So here's the reason to use H3. Cool. So how did we land on that hybrid approach? And what would you do in case you're working with, you find yourself working with geospatial systems on Databricks? First of all, you have to ask yourself some questions before you choose on the system. The first question you want to ask is, do I just want to do binning? Do I just want to bin my data into some sort of location that can be approximate and can give me a high-level overview of my system? This would lead you down that path. And for that, H3 is absolutely excellent. It gives you very high speeds to do that. It's very lightweight. So this would give you sort of a perfect outcome. Then on the other side, if you start working with multiple things and you start doing things like matching and you start caring about different types of geometries like points or polygons or lines, you probably need to touch vector space analytics in one way or another. And with that comes a few questions. So do you value scalability over accuracy, or vice versa? If you value scalability and you just want some sort of way of structure your binning or matching, or do it at fairly low precision or fairly high precision, depending on how far down you go in H3, you end up down this way, and it gives you an ability to kind of play with the resolution sizes, with hierarchical structures, gives you options there. In our scenario, we really care about accuracy. We want our data to be matched correctly. We want to match the correct roads because that assigns correct permits to trucks, right? We want to match to a correct council because that represents their area and their data and they own it. So we kind of have to go down this way. And in this area, we start asking the question of what is the scale? If you're working with a small system, you're just doing a POC or you doing it as a once-off, traditional geometrical approach is excellent. It's easy to set up. It runs really quickly, perfect for your system. In our scenario, we're working with very large-scale sort of processing. We're processing 30,000 trucks, sending data every 30 seconds, right? You get a lot of lots and lots of records. So we have to go down that hybrid approach of H3 plus geometry. So let's see how that looks. At a very high level, that structure is essentially get our position data, latitude, longitude, then get H3 index from that position data. For maps, get our polygon geometries, convert them to that WKB format to get the compression efficiency, and then tile those geometries with H3 indices. And we'll dive into that. But now you'll see that we're working with our points and we're working our geometries in the same index. So we're working with H3 now, and we can easily join the two together and kind of find those matches. So let's visualize that. Here's a set of our geometries that we've seen before. I'm just selecting them from a SQL table. What we do here, we cover them with H3, and this is a Databricks native function. So we specify a resolution 9 here, which is 100 to almost 200 meters at an edge, essentially. And this gives us a set of indices, or H3 hexagon indices, as an array, right? So for each of the geometries, we get a set of indices. And this is how it looks like in terms of the, if you visualize it. So for each array, even at fairly large resolution, you already get hundreds and hundreds of indices. So you can imagine that if you start getting higher resolutions where your hexagons are smaller, you will tile these geometries really with massive amounts of hexagons, so thousands and thousands of those. So really have to be careful about resolutions. But once we've got that, we also do our points. We get the H3 index from latitude and longitude. And here on the bottom, you can see that given a set of points with latitude and longitude, you get an H3 index back. Now that we're working in the same system, we can easily join the two together, and we know that these given points belong to these hexagons, and these hexagons belong to these geometries. So here's the answer of where your point belongs. Very similar, but ever so slightly different for roads. So those were consoles, they were polygon geometries, they were fairly large objects. Roads are lines. For them, we do the same system. We kind of convert them to binary objects. We then have to do a bit of padding, because imagine if it was a road, it was a single line in our database. We want that to, so Geoscape doesn't distinguish between 2-lane roads, 4-lane roads, 6-lane roads, and so on. So we do a bit of padding just to make sure that we capture those records that might be on the edge of the road, or I think with poor quality of satellites in Australia, sometimes it could be 50 meters off the road and it's still technically on that road. So it gets a bit tricky in the outback. But after that, it's the same principle. Convert both to H3, and now we can work an H3 system and kind of join the two together. So let's visualize that. We've got our road segments, and we've got our points. We pad our road segments. We do a default padding of 10 meters on each side, and that gives us pretty good representation of an average road. And then we do tile them with H3 indices. So we get a minimum number of H3 hexagons that would cover that whole geometry. Once we've got that, we can get the points and get H3 from those as well, and we can easily join the two together. Cool. As with all good things, they kind of can't come to an end. So the problem becomes the problem of edge cases. And this is kind of a standard thing in software engineering. Unfortunately, it crept into Geospatial as well. But you can see that there's a few scenarios here. For roads, you might have multiple roads. You might have an intersection, or sort of scenarios where a lot of them are within that single hexagon. And same for councils. You would have conditions where that hexagon is on the border between the two, and you need to figure out where it belongs. So what do we do here? This is where kind of your creativity comes to an end. You can create a lot of different approaches. For us, the most simple approach that satisfied majority of the cases, by majority being nearly 95% of the cases, was just distance. The closer you are to the road, that's probably the road you're on. So for in a situation where we get multiple road candidates in a single hexagon, we would just calculate the distance to that geometry, and that's probably which one we're going to pick. For LGAs, it's much simpler. Just check the containment, check that your point is within that object, and then you get your answer. And at this point, you're probably wondering, why would you not increase the resolution? Why not go further at higher resolution and not have these edge cases? What we found is that, particularly when you get thousands of data points, or in our case, millions and millions, you still get those edge cases regardless. You can go down to nearly highest resolution possible, and you will still find that 1% or 0.1% of cases where it sits on that edge. As a kind of fun joke, we've seen points sitting literally on that line between the two, so objectively you don't know where it is. But essentially what you start deciding with your resolutions is how can you address your 95% of cases at least amount of compute possible, and then do manual checks, or not manual, but do more expensive checks for that last 5%. So for us, these resolutions worked really well, particularly for LGAs. The number of cases where this falls into this category is 5% for our data. So for 90% of data, we process it at high resolution, get answers really quickly, but then for that 5%, we just do more expensive checks. So what do we do? How do we do these multiple matching checks? So here's an example, and this is what it looks like in the data. We've got a H3 index that matches to two different geometries, Yarra City and Boroondara City. And obviously, this is how it looks visualized. What we would do is we would do a point and polygon check. We would check that this point belongs to a polygon, and we would do it through a pandas UDF. we would take our geometry values, WKB geometry, take our latitude, longitude, pass it to our pandas UDF, and then use Shapely to do the intersect check. Fairly straightforward. Similar for roads. If you've got scenarios where you overlap multiple roads, you use the same pattern with UDFs, and you do your checks, and you calculate that distance. Instead of calculating containment, you calculate distance. Everything else is the same. So fairly straightforward pattern, but unfortunately, out of the box, it just doesn't work. There's a lot of optimization issues that we had to go through, and the reason why it doesn't work straight away is due to join explosions. So the first thing that happens is that you start with your points table, and this is going to get your latitude, longitude points plus your H3 index. And then on the other side, you're going to get your geometry table, which is your hexagon IDs and corresponding geometry to them. So once you join the two together, you end up having a much bigger table, and you also carry a lot of the geometries with you. So what you end up having is partition skew. So the example here, it has a city that has a set of customers in it, and one particular city has a lot more customers. So you end up having a skewed partition. What that means is that when Spark is processing your data, it starts with some tasks finishing within, say, 30 seconds. Some of them might take 18 minutes, some might take an hour and a half. At that whole time, your worker nodes are waiting for that last task to finish. So you get idle sort of CPU, zero CPU usage, but one of the workers is trying to finish something. So in our scenario, the skew happens because there's a lot of points, especially inside of the city, like hexagons inside the city, where there's a lot of traffic. So you'll have, say, Melbourne Central or San Francisco Central, you'll have ton of points in there that would skew your data, but then regional or faraway areas, they won't have anything. So an easy solution to that is to repartition your data after the join. There's a few ways to do it. Talk to me after the session. They're a bit more technical. You can do it through hints. You can do it through kind of explicit PySpark partitioning. But this wasn't it. So we've done the partitioning. We've got rid of the skew. And then we hit a different problem. And this one is, it's got an interesting calculation on it. But as any software engineer does, the first thing you do is not read the docs, is to throw more compute at it. And that's exactly what we've done. So when we faced this problem, we were like, how about we just spin up a massive cluster and just try have it crunch through this data? This was with client approval. That was their idea. But to give you a reference of how big that cluster was, by the time the cluster spun up, it already cost you a cup of coffee. Like, it was that expensive. So we've got that cluster spun up, started crunching through the job, and then it ran out of memory. So then we started scratching our heads and thinking, how do we solve this problem? What actually is the problem? So we did this calculation, and essentially what we found is that for an average geometry, I've shown you that it's quite large. It's about 80,000 bytes per geometry. So if you take that average, you take 300 million records that come in monthly, or 400 million, depending on the scenario. You then take the 5% of your records that you actually want to check. You end up having nearly a terabyte of data that you need to process. And that's what was happening in our cluster. It was trying to read that. It was trying to cache that. It was trying to pull it all between different nodes. So it eventually ran out of memory. And to deal with that issue, surprisingly, the easiest way to do it is to broadcast that data and have that data available to every node. So instead of carrying that geometry with your data frame, instead of carrying your geometry with your data frame here, we would broadcast that geometry and then have it available in memory and access it at runtime. There's a few technical slides on that. I can talk to anyone who's particularly interested in that after the session. But now that I've scared you with all this optimization problems and everything that we've been breaking our heads over. Databricks surprised us with, oh, actually, sorry, wrong slide. This is the difference between optimization. So unoptimized pipelines, about 3 times as slow. Optimized, much more efficient. For reference, these are compute hours. These are hours that it takes this hours on the CPU. So that's not how long the job runs. It's how long it takes to crunch the data between, say, 8 worker nodes. But yeah, luckily, if you are about to build your solutions or about to migrate to Databricks or doing any kind of new work, Databricks is introducing SD functions, and it makes all of the optimization problems that we faced a lot more straightforward and kind of just throws it out of the park. So how would you use SD functions in Databricks? Here, this code snippet is essentially the same process that we've showed you with UDFs, but now it's fully inside SQL, fully Databricks native. So the steps that are here, first we do our standard procedure. We convert our points to H3. We get that H3 index. Then we try to subset only the data that has multiple matches. So we know that a given geometry has a given H3 index. So if you see that H3 index appear multiple times in the table, it has to match to multiple geometries. So you know by default that you gotta do some processing on that. So once you've got that, what we do then is we do a whole bunch of joins within that CTE, and we take our latitude, longitude, convert it to a point. We take our geometry, convert it to a geometry object using the WKB function. And then we do a SD contains operation to just check that this point is within that geometry. Super trivial operation. You get an answer straight away. And you don't need to write any UDFs. You don't need to know PySpark or anything. You can just do it all in native SQL. Similarly for roads, pretty much the same operation. You don't need to use the limit. I just forgot to remove that. But essentially, instead of doing the containment, we do the distance computation, and this gives us that range. Databricks got a whole bunch of SD functions available. It could be distance containment. It could be intersection or overlap or any kind of thing that you might need to use. So have a look at their website. We've got, I think, maybe some slides at the end. But yeah, super cool. And straight out of the box, it just blew away all the kind of work that we spent doing optimizing that. So nearly 9 times improvement over the original sort of UDF work. Particularly, I've looked at sort of Spark plan, and I still saw that Spark is still skewed, but even though we saw skewed operations, out of the box, it's still way better than anything we come up with. So absolutely excellent sort of set of functions. So yeah, all right. Now the less interesting part. So now that we've got this solution that works with single matching, multiple matching, how do we get it to a production state? How do we build that into a system that we can develop and have it be usable today, tomorrow, 2 years after, and so on? The first thing is obviously kind of getting our maps in place. This one is fairly straightforward. This just gets your data from source to bronze layer. And all it does is that probably every 6 months or whenever you get your maps, you will load your data and you'll persist it into a set of tables. At the second step, we do that operation where we add WKB and WKT geometries. WKB for our job processing, WKT for our analysts because it's human readable. It's a text format, so it's pretty much just JSON. But we essentially give that availability to both users. The final bit is we create these H3 indices mapped to a set of geometries, and this is what we use for those join operations. Cool. So now onto a silver layer. How do we design a data model that allows us to do all of our geospatial operations. So this probably doesn't look like a star schema, but it is. This is a star, traditional snowflake schema. We've got our fact table, our position data. So this is our latitude, longitude points. And then we've got a set of dimensions that represent our geospatial matchings. So we've got our position matched to localities, LGAs, roads, and so on. On the far side there, we've got our H3 representations of the reference data. So we take our reference geometries, apply the tiling operations on those geometries, and we get our H3 tables. Probably the critical part is that you get new data all the time. City infrastructures change all the time, so you have to keep these tables in slowly changing dimensions. This one's we use SCD type 2. And for reference data, we keep track of the map version. So we know when the data was loaded. Was it 6 months, 12 months ago? And then we keep the flag whether this data is latest in the latest field. Cool. So now onto the kind of doing the actual matching operations. And for context, this is a very trimmed down process. I've cut out a lot of other work that we do on the platform. So there were used to be 30-odd tasks, but just for the purposes of matching, these are the only ones involved. So every night we run the process that ingests our position data, latitude, longitude, and we get that data into our position table. We then have our matching operations running in step 2. And all of these run in parallel because we set them up as separate dimensions, right? So we can just run them in parallel, append to separate tables, and have no concurrency issues. Another important bit is that the single matching and multiple matching here, you'll see position locality match and position locality multiple match, they can also run in parallel. The reason for that is that even before we process the data, we know that whether it will need to be checked or not, because we know which hexagons have multiple matches and which ones don't. I'm spending a lot of time emphasizing here why we want that to be parallelized. Sounds trivial, yeah, it cuts down your time, but if you think of it as a batch workload that you run every night, say today you had 2 dimensions, 6 months later you have 6 dimensions, suddenly your job is no longer 2 hours long, it's 6 hours long. By the time it finishes running, your analysts don't have the data at 8 a.m. in the morning. So you want to shrink that window as much as possible from the get-go, and this is why we try to parallelize it as much as possible. The final step there is just to do with points. These ones, we just tag anything that didn't match to a geometry as unmatched, so we don't reprocess it later on. Cool, and probably the last final bit is the most frustrating part, is what you do when you get new data, new maps come in. So as a data engineer, you probably have an analyst that comes in and says, hey, I need to reprocess this data. What we do is we ask for a window. We say, if you want to reprocess the last 2 weeks, 3 months, so on, give us that window. We'll then set, for all the tables that are dimension tables, we'll set their flag to false. So we know that this data is no longer valid because it's mapped to an incorrect map. So then in the next step, we rerun the tasks. We know that we don't need to specify a window here because we know that if the last flag was 3 months ago, we'll just reprocess data from 3 months. And then in a final step, we just do the matching. Just do the cleanup, make sure that anything that's unmatched is still unmatched so it doesn't get reprocessed. Cool. So this was our kind of path to production. Now onto Geoscape functions and all the cool stuff on the lakehouse.
Yep, I'll be quick for this one. So Databricks Geospatial Lakehouse provides flexibility to users depending on your use case and the data types, the formats you are working with. You can decide which library you want to use here. So built on open source and open standard, it supports the diverse library integrations like Apache Sedona, GeoMassa, Shapely that we used here, and GeoPanda and all that. So with the recent advancements in Geospatial SQL, we now have over 80 ST functions available, including the efficient geospatial joins, operations on the native geospatial types like geometry and geography. These enhancements support functionalities like fast data conversion, querying, and spatial join. So in terms of timeline of the spatial SQL, I steal this slide from our product manager. They were announcing it in a different room. With the DBR 17.0 onwards, you will no longer have the you're no longer required to use Python for any of the geospatial functions. And this is the last release with the spatial in private preview. And shortly after the Data and AI Summit, the public preview will start, which will start with the standard classes and then move on to serverless notebooks and jobs, and then the data warehouse shortly after. And we're targeting GA in the later of the year. Finally, in order to create the seamless end-to-end experience, our product manager is continuously working on the AI BI dashboard for maps. So we now have the point maps that allow users to render latitude and longitude points as coordinates. And then we have the core plus maps to visualize the data across the geographical regions with the shading of the colors based on the values such as the income, the population, and other metrics. History maps and other maps are coming in a roadmap. So this is an example of the core plus map. As you can see, the use case could be using that map to map the revenues and populations across different regions. Finally, Databricks apps could offer the opportunities for geospatial data apps to be rapidly developed and served to the end user. So packages like DAC-GL and its Python bindings like PyDAC can be embedded with the frameworks like Stringlet, Gradio, and Dash, which are all supported by Databricks apps. So combined with other components, you can add to your app, dynamics charts, or the plots, which you can cross-filter and drill down through the Tableau data. This could make it a powerful combination. So that's all we want to cover for this session. Thank you for joining us.